All right, great. So let's get started. So our first talk today will be by G, and he's going to tell us about a really cool new lattice technique that kind of does bootstrapping, like in FHE, but for other primitives beyond FHE.
Okay, so it's about running circuits of unbounded depth over encrypted data securely using lattices. And this is joint work with Yao-Ching and Rachel. So homomorphic encryption. So in homomorphic encryption, you can generate public and secret keys, and you can encrypt any data using the public key, and you can homomorphically evaluate any function over the encrypted data without having to decrypt it. And what you get is an encrypted version of the evaluation result. And in this formulation, the function f can be any size or depth circuit. In particular, there's no polynomial upper bound put on the size or the depth of f by the public key or the ciphertext. And this is called fully homomorphic encryption. And in contrast, there's also leveled homomorphic encryption, where you can specify an upper bound of the depth when you set up the scheme. And consequently, you can only evaluate functions that are bounded by depth d. So you can build fully homomorphic encryption from circular LWE or obfuscation, and you can build leveled homomorphic encryption from just LWE, which is a weaker assumption. Okay, so there are also many other homomorphic primitives, some of which doesn't have the homomorphic in its name, but they're all related somehow. So for all of these primitives, we know how to build a depth-bounded version of that scheme from LWE. And as the depths go up, the efficiency goes down. And for some of them, namely lockable obfuscation and homomorphic encryption, we can build it from circular LWE. And the scheme will be depth unbounded, and the efficiency will not degrade as the depths go up. However, for the other schemes, we did not know any method of getting unbounded depth except from obfuscation. And I call all of these primitives homomorphic because they can be constructed using GSW3-ish version of homomorphic encryption. And so we're wondering why there's a dichotomy between things that you can or you cannot construct using lattices. So the result in this work is that we introduce a new technique that allows us to obtain depth unbounded versions of these primitives from lattices, namely attribute-based encryption, laconic function evaluation, and reusable garbling. Moreover, for the laconic function evaluation and reusable garbling, we only need circular LWE, which is the same assumption to get depth unbounded homomorphic encryption. And the core of our technique is a bootstrapping method for the BGG plus encoding that allows you to authenticate a computation. Okay, so learning with errors assumption. So it says if you have a wide matrix and you take a random linear combination of its rows and you perturb it by a little bit, what you get, the LWE sample will look like this. It's close to some low-dimensional space. And here the arrows are small. The LWE assumption says they are indistinguishable to random things. Namely, it's as if the LWE samples is everywhere. And in the LWE assumption, we can replace the distribution of the secret R by the same distribution as the error distribution. And we'll use this version in our work. And I also mentioned circular LWE assumption. It's very similar to LWE, except you plus a function of the secret to the LWE sample. So it's called circular LWE because you can regard R as a secret key of an encryption scheme, and A bar as an encryption randomness. So the LWE sample serves as a pseudorandom one-time pad by the LWE assumption. But now you're encrypting a ciphertext of the function of the secret key under the same secret key. Therefore, it's circular. And for certain kinds of function, namely affine functions, this assumption is just the same as LWE. To bootstrap FHE, we need the function to be the bit decomposition of the secret. And this is also the version we use in our work. Okay, so let me introduce the notion of laconic function evaluation. So in laconic function evaluation, there's two parties, Alice and Bob. Alice holds a function, and Bob holds an input. So here you should think of the function as a very complex function. Its description is very long, and the input as not so long. So the goal is for Alice to retrieve function applied on the input, so f of x. And we want to do it in a way that minimizes the computation that Bob does, because Bob doesn't get any benefit from this computation. So the way they do this is to first, given a CRS that's honestly generated, Alice can compress the description of the function into a short digest, and then send this short digest to Bob. Bob will use this digest to encrypt its input, and the ciphertext will be bound to F. When Alice receives the ciphertext, she can decrypt the ciphertext using the CRS and the function description. The security guarantee is that the ciphertext of x reveals f of x, but it hides x, and it's defined using this simulation paradigm, where the encryption can be simulated using only the output of the function. And a weaker version of laconic function evaluation is the so-called attribute-based LFE. Here, the functionality changes. Alice has a policy function that outputs yes or no, and Alice also has the attribute string x. Bob has the attribute string x and also a message. And the goal is for Alice to retrieve this message if f of x is yes. So the same syntax for the digest generation, but then Bob encrypts mu with x, and here I have moved x to the subscript. There's a reason that I will talk about later. So after receiving the ciphertext, Alice can decrypt, given the knowledge of f and x, and it will output the message. The security is weakened so that the ciphertext only hides mu if f of x is no. And I have to emphasize that x is provided verbatim during decryption and it's not hidden. And therefore, the correct way to think about this is that the ciphertext contains a hash or a signature of f and x. And for this reason, it's actually possible for the ciphertext to be shorter than the dimension of x. However, it's not the focus of today, but some works I cite later will actually have this feature. Yes?
Sorry, Bob is encrypting the message with the attribute vector of Alice.
No, the reason that Alice has x is that we don't want to count x in our communication. Therefore, we just give Alice for free.
Okay.
But it's you should think of Bob as choosing x and conveying to Alice separately. And we just want to count the overhead of crypto. Okay, and despite being a weaker primitive, it's known that ABLFE plus FHE implies laconic function evaluation in general. Okay, so what do we know about lattice-based, attribute-based encryption, attribute-based laconic function evaluation? The prior construction is by Quashwicks and Wee, and they construct a depth-bounded version of ABLFE from LWE. And in this work, we construct a depth-unbounded version, and we also get rid of the dependency on the depth in our efficiency parameters. And subsequent to our work, there has been a lot of works, I'd say, constructing new versions of ABLFE for different features. There are, you can augment the functionality. So here, RA circuits means random access circuits. So these are circuits that have oracle gates that can read into a static database. It's like RAM, but it's circuit. And also, there's a series of work that tries to shrink the size of the ciphertext to rate 1. So previously this was L times polylambda, but in W24 is L plus fixed polynomial in lambda. And in all these subsequent works, building ABLV from lattices, you can plug in our version of evaluation and get an upgrade. So here, if I have this bracket, it means that there's a version that uses non-circular LWE, and you get a version that has depth dependency. And if you add circular to this assumption, you get depth unbounded plus you remove the depth dependency. So I would say that this technique is a pluggable upgrade for many works, except for the work by Abram, Malavolta, and Roy. In that work, they construct adaptively secure LFE, which is not known to be compatible with our technique. Okay, and the other notion that I have in my title is attribute-based encryption. So in attribute-based encryption, you have, think of it as access control for your operating system, but implemented in crypto. So you have a data owner who generates the master public key and master secret key. Using the master public key, you can encrypt any message with any attribute X. And using the master secret key, you can derive a restricted secret key bound to a policy F. And given the ciphertext and the secret key, you can decrypt the ciphertext if f of x is yes. So again, I have to emphasize that in this definition, f and x are provided in the clear and it's not hidden. Well, again, the same emphasize, but anyway. So the security of AB says that if f of x is no, then you cannot decrypt. In particular, ciphertext encrypting 0 or 1 should be indistinguishable to each other. And it actually has to hold even if you have multiple secret keys, as long as each of them is not individually authorizing the decryption. Okay, so what do we know about lattice-based ABE for at least circuits? Prior to us, there are, I'm sorry to not cite the ancient work of GVW, but it's superseded by BG+. So in BG+, you have depth-bounded ABE, and everything grows polynomially with D. Okay, from my mouth, the GVW has a larger secret key, where the secret key grows with the function size. Okay, and concurrent to our work, there's the work by Qini and Wei, who built a depth-bounded ABE, but with constant size secret key that does not depend on the depth from just LWE. And in our work, we need a very strong assumption. We call it evasive circular LWE, and we can obtain depth unbounded ABE without any depth dependency on any parameter. And subsequent to our work, there are again many works constructing ABE from various versions of LWE for various new features. And again, if you plug in our evaluation procedure into those ABE, you get you remove the depth boundedness, except for one work, which is by Agrawal, Kumari, and Yamada. They build depth unbounded ABE from evasive LWE, but it's a worse version of evasive LWE without circular. But okay, so and some other bits about the results in this work is that Laconic function evaluation is known to generally imply one key succinct functional encryption, which further implies reusable garbling. So in reusable garbling, you garble the circuit once, and then you can encrypt your input. And together, they will reveal the evaluation result. But in our notion, the garbled circuit doesn't hide the circuit, only the input. And from our technique, we can obtain a garbled circuit of output size and public key and the input encoding of input plus output size. Okay, and related works in this regard are this BJSS25, which builds new form of secure multi-party, not sure whether it's multi-party, but maybe it's two-party computation. And in their construction, you can plug in our evaluation to obtain a better efficiency asymptotically. And in two other works, they build succinct randomized encoding and time lock puzzles. And in these two works, I say they use our result. What I mean by that is that they crucially rely on the depth unboundedness of our evaluation procedure. So it's not just an upgrade, it's a necessity. Okay, and for the ABE, we rely on evasive lattice assumptions to handle trapdoor preimages. And there are some work studying this family of assumption, and in particular, the recent work of AM and YY actually has an explicit attack against our assumption, but it's not against our scheme. But I would say it's very close to an attack of our scheme in the form. Okay, that's it. So we're entering the technical part of the talk. To start with, I had to recap the previous work of the BGG encoding. So in the BGG encoding, for every function, you will assign a matrix that is very wide, not very wide, but wide. And the best way to think about this is that for a multi-bit output function, you have many matrices placed side by side. And the public key is the matrix for the identity function, which are sampled as random. And then the encoding is an LW sample of AF offset by a fixed matrix G, depending on the function value. And the knowledge of this LW sample, you should think of it as authenticating the fact that f of x is equal to y. We'll see how this works later. But let me introduce some good pictures. So I use this to represent an LW sample with a certain level of noise. So here you can see that I have set the noise level to be very low. And also, if I'm using formulas, I'll use the squiggly lines to represent that this term contains the noise. And the idea of these encodings and these matrices and these encodings is that you can derive from the identity function to any function, and you can derive from the encoding of x equal x to fx equals the evaluation result of f on any on this input. So this is captured in this homomorphic evaluation procedure. So given any matrix corresponding to any function, which might be a multi-bit output, you can compose it with any function whose input is the same size and obtain the matrix for the composed function. And typically, what you'll see in the paper is that you start from the identity, the matrix for the identity, and you can evaluate any single bit function to obtain AF, the matrix AF. But it's better to think of it in the first line of way. And for the encoding, you can use the. Suppose you have an encoding. Well, okay. Let me do the next animation first. If you know f of x is equal to y, then you know g of f of x is equal to g of y. And this is captured by the fact that if you know an encoding authenticating f of x equals to y, which is LW sample of under matrix AF minus y tensor g, you can apply any function g to it and obtain this the LW sample under AG compose f minus g of y tensor g. And during this homomorphic evaluation, the noise will grow exponentially with the depth of the circuit. Okay, so with this encoding, I can describe the previous construction of depth-bounded ABLFE. In this ABLFE, the CRS is just a matrix for the identity function, plus another random vector u that we will use to produce one-time paths. The digest of a function is the matrix corresponding to that function. And since the policy function is just one bit, you get a fixed size except it depends on the depth. And then the ciphertext has two parts. The first part is an encoding authenticating the input is this particular x value. And the second part is this very weird LW sample under AF times G inverse of U. Then you use this value to one-time pad the message. And we'll see how it works. So suppose f of x is equal to 0, in which case we will be able to decrypt. Then you can do the homomorphic evaluation, which will give you s times AF minus fx times G. But fx is 0, so it's just SAF. And then you can multiply with this short vector G inverse of U, and then you can cancel the one-time pad. And when f of x is equal to 1, you can still do this homomorphic evaluation, which will give you this encoding plus s times u, because you have this minus g here. Sorry, it's actually minus, but the proof will be the same. So if you just rearrange this equation, you know that this purple one-time pad is equal to homomorphic evaluation plus LW sample, which is going to be pseudo-random under LW assumption. So that proves the security. And let's see why this scheme is depth-bounded. It's very simple, because the noise grows exponentially with the depth, so the noise bound is 2 to the d. And 2 to the d had better be smaller than the modulus of these matrices. And since the CRS contains at least one element from ZQ, therefore it's the depth will be smaller than the length of the CRS. So how can we get unbounded depth? In FHE, we know that we can reduce the noise during our evaluation. And it's the same idea here. We can try to reduce noise to achieve unbounded depth evaluation. So for that, let's recap how FHE does this. Suppose we start with a ciphertext, a fresh ciphertext of x. You can do homomorphic evaluation to obtain f of x ciphertext, but it will have a moderate amount of noise. Then you can evaluate another function. It will have a large amount of noise. It's still decryptable, but it's about to overflow. So if you try that again, your message is flooded, so cannot decrypt. The solution is to go back to the moderate noise when you are still capable of decrypting. Therefore, it's something like this. So the way FHE does this is that you can assume circular security, and you encrypt the secret key under itself. It will be a fresh ciphertext. And then you evaluate on this fresh ciphertext. The function you evaluate is the decryption function, taking the input as the secret key. And you hardwire this ciphertext that's about to overflow. And if you apply this function to the secret key, you will obtain basically the decryption result, which is the message under the ciphertext with large noise. But the noise in this evaluation will only be related to the complexity of the decryption algorithm, which is a fixed value. Therefore, it will not, under appropriate parameters, it will be in the moderate range. Therefore, we have achieved the going from large noise to moderate noise, and then we can do this evaluation again and again. So let's try applying this idea to the AB encoding and see what happens. Suppose now I have an encoding of fx equals y, but it has a very large noise. So given this encoding, and suppose I also know S, and I also know AF large, then I can do what I call attribute decryption, attribute decoding. Basically, it recovers Y. How to do that? You just subtract S times AF large from this encoding and see whether it's close to 0 or it's close to very large. So mimicking the FHE idea, let's suppose we have a circular encoding which encodes the LW secret that's used to do the authentication. And let's try evaluating the attribute decoding function on this encoding. Well, we just plug in S into this, and since the the encoding with large noise has value y inside it. The evaluation result is, of course, y. Therefore, you get an encoding with moderate level of noise, encoding y, except it's a different matrix, AF. So the idea is, well, I can define this as the encoding of the fact f of x is equal to y, and just try to do the evaluation from there on. However, this has two problems. The smaller problem is that evaluation requires the knowledge of the attribute under it. Therefore, you have to know S. But knowing S will destroy all security because, well, there's no pseudo-randomness. The bigger problem is that this function, the description of this function you evaluate depends on the encoding CF large. The encoding happens after you compute the digest, or after you do the evaluation of public key. Therefore, actually, you cannot do any evaluation of the public key. Namely, you don't know what AF is if you don't see the encoding. And it's going to be a different AF for each encoding. So that's very bad. OK, now I'll introduce our method to deal with it. It's going to be a different order. So we'll do noise removal, but it's somewhat not very easy to think about. So I'll just describe its property abstractly first, and we'll go from there. So remove noise will take as input a vector that's the same shape as a noise, as an LW sample. So it's going to be LW sample. This is going to be a low depth function, and it satisfies this gigantic equation, but don't worry, I'll explain it. So this is the remove noise function. It's a broom. And then if you put an encoding into it, with put an encoding with very large noise, but still not flooding the encoding at all, then with high probability, we'll spit out two things. The first part is you remove noise from a version of the encoding without any noise, and authenticating the value being 0. But of course, we know that value is not 0, it's y. So the payload goes to the second part. OK, so let's see what we can do with noise removal. First, we have the payload. That's part of the structure we need for the homomorphic evaluation. However, this first part, it's noiseless. However, you cannot do any homomorphic evaluation on it. So the idea is to compute something else in order to revert it into the format of BGG encoding. So the easiest thing is to compute something minus this. And the something should be SAF. And I'll define, well, the idea is to come up with a way that computes something like this for any AF. And I'll define whatever AF that comes out as the AF for this function. OK, but before that, this part, remove noise of no noise encoding, has some good properties. First, it's low depth, because remove noise itself is low depth. And this function is also fully described by AF prime. It's independent of the encoding. That's the crucial part. OK, now we're going to proceed to compute this SAF minus remove noise noiseless. And for that, we'll need other previous works. We need Gentry's Sahai-Waters FHE scheme. But the thing you need to know is that its secret key is an LWE secret. Its ciphertext has the same shape as an LWE public matrix. And then you can consider vector-valued functions, where the vector is of the shape as an LWE sample. And then if you do the homomorphic evaluation on such shaped vector-value functions, what you get is another ciphertext, which happily has the same shape as an LWE public matrix. And then for the homomorphically evaluated ciphertext, you will have this decryption equation, which is if you multiply S with the homomorphic ciphertext, you get a noisy version of F, of the vector that you're evaluating. OK, I have to remind you that there's no such thing as coincidence. Therefore, all those shapes, all those names of the symbols are going to have a are going to be very useful. They're going to collide. Okay, and we also need the BTVW attribute homomorphism, which is an extension of the BGG homomorphism. So previously, we can do homomorphic evaluation for any Boolean function, but now we can do homomorphic evaluation for matrix-valued functions, where this matrix is also of the same shape as an LW public matrix. So if you do the public key evaluation on the master public key, you will get the matrix corresponding to this matrix-valued function, which will also have the same shape as the matrix for a one-bit function. And for the encoding, you can also do the homomorphic evaluation. What you get is, instead of minus fx times g, you just get minus fx. And note that this computation is actually compatible because fx and af has the same shape. And also, the BGG evaluation can be recovered by setting f of x equals little f of x times g. It's going to be the same thing. Okay, with those two tools, we're ready to do the format restoration, which is to compute this subtractive term. For this, we'll need two new things. First is the circular ciphertext, which is something we see in FHE, which is encoding S under S. And we also need a circular encoding, but it's different from the previous version. So previously, we encoded the bits of the LW secret as attribute, but now we're encoding the ciphertext of the secret as the attribute. Okay, so now let's do homomorphic evaluation on it. The ultimate goal is to compute. The ultimate goal is for the remove noise function to come out as the evaluation result. And since the attribute is the ciphertext of little s, therefore we will evaluate the homomorphic evaluation of remove noise function, which I will represent using two different colors, very important. So this will take the place of big S, which is the ciphertext. This will take the place of little s, which is the LW secret. So if you evaluate this, what happens is that according to the matrix homomorphism, you get S times A little f minus big F, where big F is this function applied to the attribute S. Therefore, it's blah, 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 but you replace the blue underline by the blue S. Okay, now you can use distributivity to split out those two terms, and I will put the homomorphic noise from eval CT into the first term. So the second term is little s times f, and if you still remember from 2 slides ago, this is decryption. So this will be little f, where little f is the function being homomorphically evaluated, which is remove noise of something times af prime. And this something is the ciphertext, is the plaintext under the ciphertext big S, therefore it's the little s. And this is known as the dual use technique in BTVW, and I call it automagic decryption. Okay, so, well, we have finished the task of restoring the format because we have computed SAF minus the remove noise function. And let's do some quick check. First, the function that's being evaluated PK is fully described by this matrix AF prime. Namely, it's this function, heval of remove noise of, but the parameter here is AF prime. It has nothing to do with actual encoding. This function is low depth. It's also a fixed depth function. And therefore, it will yield moderate noise instead of very large noise. And lastly, it only directly uses the ciphertext of S, not the LW secret S. Therefore, we can hope for security. Okay, so to complete the picture, I also need to tell you how to remove the noise. The idea is to convert LW samples to learning with rounding samples. and then you restore the modulus. So if you divide by a big number and round to the integers, then you will shrink the modulus. But then you can restore the modulus by just multiplying the value that you have just divided. So it will look like this. Okay, so for the derivation, please bear with me. First, what you have to do is to split out this big G out of the rounding. So here we're ignoring the small entries in G, and I will set the m, which is the value I divide, to be a power of 2. Therefore, most entries of big G are going to be multiples of m. Therefore, you can take them out of the rounding for free because they are integers anyway. And then the next is to note this, the noise value is large, but it's not that large. Therefore, it will rarely hit the boundary of carry and borrow. Therefore, you can just remove it from the rounding, and the rounding result will not change with high probability. Okay, after this, you just multiply, So after this, what you obtain only makes sense mod q over m. So the next thing you do is to multiply by m and restore the modulus to q. And you will get, well, the first part is just going to be the remove noise function applied on a noiseless encoding. And the second part is the payload. However, there's a small issue. First is that we ignore the small entries in the G when we take the G out of the rounding. And this also leads to having an incomplete G in our output. So we're going to fix the incompleteness of G. Okay, so what we just did is part 1, which deals with large entries in G. What we do is to divide by m, round, multiply by m. For the small entries in G, we just swap the order of divide and multiply. We first multiply by m, so that it's always a multiple of m, and then I divide by m, and then I round. So it's kind of confusing. First, how can you multiply a large number? That will blow up the noise. Second, what's the point of dividing by m after multiplying by m? That will just cancel out. Actually, that's not the case, because when you multiply a number, you always multiply G inverse of the thing that you want to multiply. Therefore, the way you deal with the small part is to multiply the encoding by G inverse mgl, then you divide this quantity by m, then you round. So for now, please just focus on what happens to the G in this equation. So what happens is that G times G inverse of mgl is going to be mgl. And now the denominator and the numerator both have m. Therefore, you can just remove m and take this value out of the rounding. And that finished the description of our noise removal function. Okay, so I know it's a lot, so let's have a bird's eye view of the noise reduction procedure. I'll use the 3 colors to represent encodings having small or moderate or large noise. So suppose you're in the middle of homomorphic evaluation and you have moderate noise of 2 gates. Then you want to apply another gate. You first do the BGG evaluation, which will give you an encoding of the output gate, but it will have large noise. Then you perform the remove noise procedure, which will spit out something that doesn't allow you to do further homomorphic evaluation, plus the payload. And then we want to restore the format by eliminating the remove noise, which we do using the circular encoding. Using the circular encoding, we can homomorphically evaluate the remove noise function, which will spit out SA3 minus the remove noise term. And then you cancel those 2 remove noises, and then you restore the format. Moreover, the output encoding will have moderate noise because the noise fully comes from the evaluation of the circular encoding, which starts from fresh. Okay, and then you can do this infinitely many times without any restriction on the depth. Okay, so if we go one more level up, it's a very good abstraction. This abstraction is actually used in the follow-up works. oops, oh, sorry, this should be u eval pk. So if you have a function and you have a matrix, well, it should be AID, but A attribute is just AID, and you have a circ, which is the public matrix you use to authenticate the circular ciphertext, then you can obtain a matrix corresponding to the function f. This matrix will have size, modulus, and dimension, both independent of the depth and size of f. And then you can do this unbounded evaluation of ciphertext. But now you have to, in addition to the fx and then the public matrix and then the encoding, you also have to provide the circular ciphertext, the public matrix for the circular encoding, as well as the circular encoding itself. And this will give you a moderate noise version of the evaluation result with high probability. Okay. And I think I'll conclude my talk by just summarizing what we did in this work.
Just a question, is the circularity assumption pretty much the same as GSW?
It's exactly the same as GSW.
I'm not quite exactly sure. I think GSW circular is quadratic. This might be cubic. It
What do
might
you
be
mean?
cubic function encrypted inside. If the big S is the GSW itself is quadratic, then you have an additional S multiplied to it. So
Oh, on the last line.
yeah.
But you're hiding it by a circ, so that's just a random matrix. Because a circ minus bits S is just random.
You can, the idea is to program the A circ that the adversary sees.
Right, it's just.
I think
So those are just LW samples, but you tell the adversary the matrix is actually whatever you receive plus bits of S.
I see.
the potential difference with GSW is that we need to use S with small norm, and it's not necessary in GSW.
Sure.
But yeah.
Yeah, that's a good point. Please.
Yeah, so I think your the basic LW assumption, this scheme right on is defined as a circular public coin version, right?
Yes.
So like is there any difference between the circular like a public or coin version of the indistinguishability or like a private coin indistinguishability such that our target matrix P also includes like A minus like bits of the circular encryption of the secret S. So my point of the question is like, can we also regard the publicly or circular public coin or indistinguishability as a one example of the private coin indistinguishability, which includes encoding includes the circular FEG encryption of the secret key, or is there like more difference?
I think you can definitely formulate the evasive circular LW as a version of, it's a very different version than the usual private coin, because in the usual private coin evasive LW, you're not allowed to touch the secret, the LW secret. Therefore, you will not be able to compute the circular ciphertext in your sampler. But I could conceive a version of evasive LW where you allow the sampler to prescribe the distribution of the secret as well as leaking some information about the secret.
So I think in the private coin version, maybe my understanding is incorrect, but like, I think sampler can also add the secret matrix S sampled from some private coin along with like a matrix P, which is used for like a target of the preimage sampling. So
There's no gold standard on the definition
Ah,
of that
yes, yes.
coin.
Yeah. Well, let's just say if you use Hotek's original version of evasive LW, then you cannot do that. But I do remember seeing some versions of evasive LW where you can specify the distribution of the secret.
Yeah, thank you.
Okay. Cool. Let me finish the concluding slide. We introduced the bootstrapping technique for attribute-based attribute encoding and enable homomorphic computation to unbounded depth. And this implies lattice-based depth unbounded laconic function evaluation, one key succinct FE, and reusable garbling, and also attribute-based encryption. So some very fascinating open problems left by this work are proving ABE security from falsifiable assumptions, which means you cannot do evasive LWE. Maybe we can do it from circular LWE. And then coming up with a version that allows polynomial modulus to noise ratio. And also whether you can do bootstrapping in a non-circular way. Okay, that concludes my talk.
Another talk coming right up, and maybe we can take questions as the speaker sets up.
Sure.
Let's thank you again.